Hello everyone. This lesson will talk about the most noteworthy application of cryptography of the recent decade, the cryptocurrencies. In this lesson, you will hear about the origins of cryptocurrencies, learn what a blockchain as a data structure is, and the various cryptographic algorithms that make cryptocurrencies possible. Cryptography puts the crypto in cryptocurrencies and constitutes their very nature. This lesson will focus on cryptocurrencies as an application of cryptographic algorithms and will omit the financial side of things. Initially, the Achilles heel of digital currencies was their vulnerability to counterfeit, specifically the double spending problem. It occurs when the same unit of crypto has the potential to be duplicated and spent twice. Like each government has anti-counterfeit measures for physical cash, a central trusted authority in digital commerce can certify legitimate coins, but in a decentralized system it is significantly harder. In 2009, a pseudonymous person or a group of people going by the name of Satoshi Nakamoto suggested a way to solve double spending problem. Their solution was using a peer-to-peer distributed ledger that is time-stamped, secured by cryptographic means, and implements a consensus algorithm for all the peers to keep track of spent coins. This led to the creation of the blockchain that is known today. Bitcoin was the original and the first cryptocurrency, and at the beginning the only blockchain. Nowadays there are hundreds varying in the algorithms they use and in the utility they provide. The examples in this lesson are going to be mostly based on Bitcoin. Blockchain and cryptocurrency are terms often used interchangeably. They are inherently interlaced with one another, but are two distinct technologies nonetheless. A blockchain is a decentralized public ledger. From a computer science perspective, it is essentially a data structure. It is a distributed type of a database where all the data stored is separated into blocks. Once the data is written to a blockchain ledger, it is immutable. Data events on the blockchain are commonly called transactions. Each transaction is time-stamped and included into the blockchain in its chronological order. In the case of cryptocurrencies, transactions usually transfer funds and contain the sender, receiver, and the amount to be transferred. And every block is a set of such transactions. The number of transactions saved per block may vary depending on the implementation and number of users of a particular blockchain. For instance, on Ethereum, the latest block contains around 300 transactions, while the latest block on Bitcoin stores about 10 times as many transactions. Every next block on the blockchain references its previous block, creating a chain of blocks. Only the very first block, the so-called Genesis block, has no reference to the previous one. Many different entities, called hosts, peers, or nodes, operate a blockchain. These peers do not know or trust each other, and they have no need to trust each other since many peers keep a copy of all data and no single peer has the power to change or censor that data. The nodes constantly communicate to keep each other updated on new transactions and blocks. No centralized entity is responsible for accepting and processing new transactions. Any entity can create a transaction as long as it's in accordance with the rules, the protocol of a particular blockchain. This transaction is then broadcast to every node. The number of copies makes the blockchain slower than a regular database, but it has the advantage of independence from a single authority and is constantly verified and updated by all the computers in the network. Cryptocurrencies are virtual currencies that operate through a decentralized blockchain and rely on cryptographic mechanisms for security. Blockchain is not an optional technology for cryptocurrency, but a foundational feature. A large draw of cryptocurrencies is their security and transparency on the blockchain. Blockchain transcends cryptocurrencies, as the latter are merely an application of the former, just as they are an application of cryptography. The merit of cryptography is that digital economies can function without the need for a trusted third party. The two main cryptographic mechanisms used in cryptocurrencies are hash functions and public key digital signatures. Hash functions serve as a guarantee of the immutability property of the blockchain history of transactions. As you already know, hash functions are used ubiquitously for providing data integrity in information systems, and they serve the same purpose in blockchains: to ensure the prevention and detection of the alteration of data, whether unintentional during transport or malicious. When a block is written to a blockchain, its contents are hashed and the hash checksum is saved as well. Hash is also used to uniquely identify each block on the blockchain, so that information contained in any block can later be retrieved using its hash. These many zeros that you see in the block hashes are not coincidental. They are a part of the Bitcoin's proof of work consensus mechanism. To commit a new block to the history of Bitcoin transactions, a peer must discover by brute force a nonce value that, when included in the block, will result in an acceptable hash that is less than or equal to the current target set by the Bitcoin network. This process is called mining. The miner is rewarded some Bitcoins for performing this computation. At the time of writing, the target hash value was this. You can easily confirm that the preceding block hash is below this value. Target hash value on Bitcoin is adjusted about every 2000 blocks to keep the speed at which new blocks are mined roughly constant, a block every 10 minutes. As soon as the new block is added to the blockchain, its history is sealed. If at a later point someone tries to change the transaction included in this block, for example, Mallory says that Alice sent her money instead of Bob, the block hash will no longer match. If this hash does not match, the nodes operating the blockchain will mark this block as invalid and reject it. Moreover, since the next block contains the previous block hash reference as well, it will become invalid too. This way, an attacker who wants to rewrite information already saved in a blockchain will have to rewrite not only the whole block that contained that particular piece of information, but also every block that was added after it. Changing the history of blocks is possible if the hackers manage to gather more computing power than the rest of the peers in a blockchain network. This is called the 51% attack. In this case, a group of nodes become a dominant majority and can seize control over transactions and the blockchain history, effectively destroying decentralization of the network. Such attacks are easier to carry out in the early stages when the nodes participating in the network are relatively few. For instance, Bitcoin risked this situation in early 2014. But it becomes increasingly more difficult as new nodes join the network and the blockchain grows. Transfer transactions of Bitcoins and other crypto coins require an alphanumeric sender and receiver account identifiers, similar to the international bank account number in a centralized banking systems. However, in a decentralized cryptocurrency networks, these identifiers are not predefined or assigned by an authority, but every user generates them for themselves. To be able to send and receive funds, Alice first needs to generate a private and public key pair. Cryptocurrencies use elliptic curve cryptography for this purpose. For instance, Bitcoin uses the SCP-256K1 elliptic curve. Her public key is then encoded into a Bitcoin address that she can share with others and receive coins. As you already know, exposing the public key does not put her private key at risk, since it's practically impossible to obtain the private key from the public due to cryptographic properties of elliptic curves and the discrete logarithm problem. Alice needs to save her private key somewhere no one else can access it, and she can always recompute her public key from the private key when needed. since these addresses are generated randomly by each user, they are anonymous and have no meaningful connection to the user's identity, unlike the conventional bank accounts. One person can create an unlimited number of addresses, further increasing the anonymity of the payments. In practice, a new address is often created for every next transaction, and the funds are withdrawn within hours. Alice's private key is essentially her password, providing access to this account and the ability to perform transactions with currency, so it has to be stored securely. The tools to store and manage private keys are often called wallets. The multiple common types of wallets, ranged by security and reliability lowest to highest, are online on a cryptocurrency exchange platform, software wallets on a computer or a smartphone, printed paper wallets, or offline hardware wallets. When you own cryptocurrencies, what you really own is a private key associated with an address that stores funds. Whoever has a knowledge of that key can spend the funds. If the private key is stolen or lost, or it was stored on a device that breaks, there is no bank or institution to reset it, and the access to the respective cryptocurrency account is going to be lost indefinitely. Every outgoing transaction has to be authorized by the sender account holder. Before submitting the transaction to the blockchain, it is digitally signed to ensure that only the owner of the account can perform a transaction using their balance. Verification of a signature effectively means that only the owner of the private key that generated the public key could have produced the signature on the transaction. Digital signing provides non-repudiation. The signer, as the only owner of the private key, cannot at a later time claim that they did not sign this transaction, because no one else could have signed it. Alice cannot send Bob bitcoins and then say she did not intend to and ask Bob to refund them. This is another reason why the private key associated with the cryptocurrency account has to be kept secret. If someone else gets hold of it, they can sign a transaction that authorizes a withdrawal of your funds or a transfer to a different account, and there is no way to undo that transaction or claim the funds back. Digital signatures in cryptocurrencies also ensure integrity of the transaction. Once the transaction is signed by the sender, no one else can change its contents, recipients, or amounts. Cryptocurrencies are yet another example of cryptography influencing lives at scale, with the growing adoption of blockchains and cryptocurrencies across industries and borders. Cryptography will keep evolving to meet the demands of the digital finance era for a secure environment.